acts on a vector, okay, and it preserves the rank of the vector. Okay, so now if I consider, before going to the SU2, let's consider the set of unitary matrices. Okay, so if I am having the unitary matrices, what is the condition for unitary matrices? U dagger is equal to identity and U dagger U is equal to identity. Is this the condition? Okay, now if I take the set of all matrices that are satisfying these conditions, okay, that means I am taking the set of unitary matrices, okay, they form a group under matrix multiplication, okay. So what I am saying, I am having here actually U, that group we call as a UN group. N means the dimension of the matrix, okay. Let's take n cross n matrices which are unitary and they form a group under matrix multiplication, okay. So I am having, let's say, some U, okay, and U dagger U, that's equal to identity, and U dagger is equal to identity. They can be the same thing, they can be different. It's not necessarily U dagger is same as U dagger U, okay, it's not necessarily true, okay, but okay, for our use, we can take U dagger U is equal to U dagger, okay. So this forms the setup, okay, so this forms a unitary group, okay, and n is the dimension of the matrix, clear? Samajh? Okay, now if the determinant of this U is 1, if determinant of U is equal to plus 1, it can be minus 1 as well, okay, determinant of U can be minus 1. If you take the determinant of this thing, this very object. So what is the determinant of this U dagger? So that's equal to determinant of identity, clear? So this I can write determinant of U multiplied by determinant of U dagger, that's equal to 1. Determinant of identity is 1. What is the determinant of U? That is same as determinant of U dagger, clear? So it is simply determinant of U square. So that's equal to 1. It implies determinant of U has to be equal to plus minus 1. But we are taking determinant of U to be equal to plus 1. Then we call such group as SUN. Special unitary group in n dimensions. Clear? Now we consider here n is equal to 2. So that we call as SU2. Clear? So we'll do a detailed analysis of this SU2 group. Clear? So now let's consider, okay, so what I need to consider, what is the element of this SU2? First tell me. Okay, let me take only U2 for the time being. What is the element of U2? It's a unitary matrix, 2 by 2 unitary matrix, clear? It's a continuous group, huh? Okay, you will see it's a continuous group. We are actually doing the continuous groups, huh? Okay, so you can think it in the analogous way what we have done for the rotation group. Okay, rotation matrices are what? Orthogonal matrices. And you know the rotation is simply, you can move from, let's say, from one angle to the another angle in a continuous fashion, is it? Similarly, unitary groups, unitary matrices is actually a generalization of a matrix to the complex vector spaces. Clear? So, orthogonal groups belong to the real vector space, you can think, okay, and the unitary matrices belong to what? Complex vector space. Unitary, you can think a unitary transformation as a rotation in the complex vector space. Clear? Samajh aaga? Okay. So now let's write, okay, so let's take the element of the group. Okay, let's call that element as U. Okay. So let me take an arbitrary element for the time being. Let's say A, B, C, D. Okay. And now I want this matrix to be unitary. Okay. You got my point? So now, what is U dagger? Tell me. So these are complex entries. A, B, C, D. These are the complex entries. Okay. So what I am trying to figure out is that I need to okay, I want to get a general unitary matrix in 2 dimensions. Clear? Or in other words, I want to get a general 2 cross 2 unitary matrix. Clear? So if I am taking a unitary matrix, its entries are complex in nature. In general, you can put the entries to be what? Complex. But if I take a rotation, let's say, plane rotation in, let's assume in 3 dimensions, what are its entries in general? They are real numbers. Clear? So this is the distinction between two vector spaces. Clear? Okay, so what is the U diagram? Now tell me. So it is A star, then it will be B star because you need to transpose as the C star, D star. Clear? Okay. So what is the condition of the unitary tree? Okay, tell me. What is the condition of the unitary tree? Okay, so our condition is U dagger, that's equal to identity. Clear? Or in other words, I can write this U dagger is equal to U inverse. The inverse of the unitary matrix is what? Its dagger. Clear? So, okay. So now let's write what is U dagger. So or I can write this as A star, okay, C star, D star, B star. Okay. So that's equal to what is the inverse? Now tell me. So inverse, what is the inverse of U? 1 divided by determinant of U and the adjoint matrix. Clear? So now let's calculate. So you will be having determinant of U, okay, multiplied. What is the adjoint? So you need to calculate the minors. Okay. So what is the minor of A? That is D. Now what is the minor of B? Minus C, is it? Okay. So it is minus C, then minus B, and what this is? A. Clear? Okay. Now we impose one more condition. Now if determinant of U that's equal to 1. So this is equal to 1. Clear? समझ आया? Okay, so no. So when I take the minors, I need to take the transpose as well. Because you need the minor. So how I define the inverse of a matrix? So it is 1 divided by determinant of A and adjoint of A. This is actually what? So minor matrix, it's transposed. Clear? Okay. So it is actually B and minus. Is it? Okay, because you need to take the transpose as well. That is how we define the adjoint. Now if I impose determinant of U equal to 1, what it gives me? This is equal to 1. So it implies, now compare the matrix elements. So you will be having A star is equal to D and D star is equal to A. Diagonal terms, is it? Clear? Now what is now C star? C star is equal to minus D and B star is equal to minus C. Now you can check they are actually consistent, is it? So now what it means? You can put C star equal to minus B, or in other words you can take C to be minus B star and D as A star. Clear? So now we have figured out the general matrix. Okay. So what is a general SU2? So now tell me. So that's actually equal to. Now tell me. What is it? So it is A for, okay, so let me write B. Okay, what is B? Here it is C. What is C? It's minus D star. What is D? It is D star. Clear? Now tell me what is determinant of U? So that's equal to mod of A square plus mod of B square, and that's equal to, so this is the determinant of A. Clear? So now tell me how many parameters here are? How many parameters will specify this element or this group? Now look here. So you started with this object A, B, C, D, is it?
Yes, sir.
So A is a complex number, B is a complex number, C is a complex number, D is a complex number. Clear?
Yes,
so now how many total parameters are? 8. Because a complex number comprises of how many units? Two real numbers, is it? You can specify a complex number by 2 parameters, is it? 2 reals. So how many elements are there? 8, is it? Clear? Now tell me how many are now remaining? More. Okay, so now look here. Huh? No? So how many are they? Two. How many are they? Two. This and this, they are the same. They are simply complex conjugates. And A star is the conjugate of this thing, is it? So you can see it from here. So how many equations are there? Huh? Yes? 4 equations, is it? So 8 minus 4, how many? 4, is it? So but there is additional constraint. Is it? So determinant of u is equal to 1. Clear? So this is an additional constraint. How many are now remaining? 3. Okay? So that means this is specified by how many parameters? 3 parameters. How many parameters specify the rotation group? 3 parameters. Theta, phi and psi, is it? 3 angles specify your rotations in 3 dimensions, is it? And here also how many parameters will specify me the rotation in 2-dimensional space? So you can think this unitary operator this way object as a rotation in 2-dimensional space. Clear? And that's a complex vector space. Samushyama? So how many parameters specify that rotation? 3 parameters. Clear? And we are trying to figure out that. Okay? Got it? Okay. Okay, so now let's look at the rotation group. Suppose if you are having the rotation R, it acts on this vector R and you get what? This R prime, is it? So this rotates this R. R is a column vector, clear? It's a 3 column vector, it is having 3 entries. Now since you are in the 2-dimensional space, okay, so now I need to specify a vector on which this unitary operator acts. Clear? And we call that as a 2-signal. Huh? Okay, so what I mean, okay, so these elements or these rotations in 2-dimensional space act on certain vector having only 2 vectors. Clear? So now let me define that vector to be zeta having 2 entries. Okay, so you are having, we call it as a 2-signal. So let me write only signal. It's in a 2-dimensional space. What I mean by that, okay, so you can think, let's say you can write A and B. Okay, so it is having 2 entries. Okay, so let me give you an example. Suppose if you are having an electron, okay, so think it's spin. What is the dimensionality of the spin space for a single electron? 2-dimensional. Is it? It can be either up or down. Clear? So there are only 2 possibilities. You can write, let's say, up spin state as, let's say, 1 0 and down spin state as what? 0 1. So these are the signals, 2 signals corresponding representing your electron. Clear? So it can be the linear combination of the 2. Okay, so it can be, let's say, along x-axis, plus x-axis or the minus axis. Okay, so here I have considered as the z-axis. Huh? So Samashyama? Got it? Okay. So now how it acts on, let's say, okay, so this u acts on this zeta and you will get some zeta prime. So that means under SU2, okay, okay, the way, so I can write, let's say here under, okay, under O3, your R transpose what? Goes to R prime. Samashama? So because R is what? What is this R? This is an element belonging to O3. Samashama? So here I am taking U to be the element of SU2 and it will rotate your 2-dimensional vector. Clear? So it will give you, it will form a new vector. Clear? Simply just the transformation. Okay, so now let's try that. So or I can write zeta 1 prime, zeta 2 prime. So that's equal to, what is U? It's A, B minus B star and A star. So acting on zeta 1, zeta 2. So what is that equal to now? So zeta 1 transforms as A zeta 1 plus b zeta 2 and zeta 2. So this is how the components of this vector undergo a transformation under this SU2. Okay. So then you are having this minus zeta 1 plus a star zeta 2. Okay. If you are having some difficulty in understanding this, think of a rotation in 2 dimensions in xy plane. So how the components of a vector change? X prime goes as x cos theta plus y sin theta, is it? And y prime goes as minus x sin theta plus y cosine theta. You can think those sines and coses as a and b here. Samajhama? And x and y to be the zeta 1 and zeta 2. Clear? Okay. So now let's look under this SU2. So let's look at the length of this very vector. Okay. Okay, let's look how I define the length of the vector. First, let's write the length of the vector. Okay. I should not write length, the norm of zeta. So let me put norm of zeta. So that is how I will write. Can you tell me? So think this as, okay, think it in terms of the cat, vector cat. Okay? So what it will be? So it will be simply zeta. Clear? So this is the norm. So this is same as actually zeta dagger, zeta. So what is zeta dagger? Now let's write the zeta dagger. So it will be zeta 1 star, zeta 2 star and zeta 1, zeta 2. So how much is that? So it is mod of zeta 1 square plus mod of zeta 2 square. So this is the norm of zeta of this very vector. Now let's look at the how this norm varies under SU2. Okay. So under SU2. So now let's check. Since my zeta goes as zeta prime u zeta. Okay. Since u belongs to what? U belongs to SU. Clear? So what will be now? The zeta dagger. Now let's take the zeta dagger. So it will go as zeta prime dagger as dagger of this thing. U zeta dagger. So what is that equal to? Zeta dagger, u dagger. Clear? The dagger means, okay, so you need to take complex conjugate with the transpose. Okay. So now let's write therefore norm. So let's write zeta dagger zeta. So this goes as zeta prime dagger zeta prime. So that's equal to zeta dagger u zeta. So u dagger u is identity. That is zeta dagger zeta. So what it means? Norm is preserved. So that means the length of the vector remains invariant. Got it? So now let's take the under any transformation, any unitary transformation, length of the vector will be always preserved. It will remain invariant. Okay, so under any orthogonal transformation, the length of the vector will be preserved. Okay, clear? So it will remain invariant. Now let's look at another kind of quantity, what we call the outer product. So if I am having some state, let's say outer product means like this. Clear? So this is actually, what will be the outer product here? So it is zeta and multiplied by zeta. Clear? So this is the outer product. So you multiply, okay, cat with the, it's actually the projection. It's an operator. Got it? Got it? Okay, now look here. So this is an inner product. Okay, this inner product is a number. Clear? So this is an outer product and it's a matrix. It's an operator. So now let's write what is zeta. Tell me. So zeta is zeta 1, zeta 2. What will be the zeta dagger? Zeta 1 star, zeta 2 star. Clear? This is the dagger. Now you can see it is a matrix. So it's mod of zeta 1 square, zeta 1, zeta 2 star, zeta 2, zeta 1 star, and mod of zeta 2 square. Clear? Is this a matrix? Huh? Okay, now let's look at the transformation rule of this outer product under SU2. Okay? So now let's take a transformation that belongs to SU2. Okay? So what will happen? So this zeta dagger goes as zeta dagger prime. So how much, what is zeta prime? So zeta prime goes as u zeta and zeta dagger goes as zeta dagger u dagger. Clear? So what is that? So it is something u. So that means this matrix under SU2 transforms as u matrix into that. Clear? So this is how the matrices will transform. Got it? So this zeta dagger is an operator. Huh? Okay? So we will not call it as an operator. We will simply call it as a matrix or the outer product. Clear? Okay. So now if you see, okay, now let's try to figure out the transformation rule for the zeta dagger. How the zeta dagger transforms, is it? So we know the zeta dagger transforms this way, is it? But we have not calculated it explicitly. We have just written it in this fashion. Now let's look it in terms of in the element wise. Okay. Okay, so let me rewrite this thing. Okay, so our zeta, so let's take this u belongs to SU2. Okay, so zeta goes as zeta prime as u zeta. So which implies we have just calculated zeta 1 prime is equal to a zeta 1 plus b zeta 2, is it? And zeta 2 prime is equal to minus b star zeta 1 plus a star zeta 2, is it? So this is how the elements of this vector zeta transform. We have just seen it. Now let's look at zeta dagger. So now we have this zeta dagger. It goes as zeta, okay, so zeta dagger prime. So how much is that? So it is simply zeta dagger u dagger. Clear? Now let's calculate the elements. So what is this zeta dagger? So it will be simply zeta 1 star prime, zeta 2 star prime. Clear? Clear? Zeta dagger is what? Zeta 1 star and zeta 2 star as a row vector, not as a column, because there is a dagger. So now what is the zeta dagger? So it is some zeta 1 star, zeta 2 star. Clear? And what is u dagger? Now tell me. So it is a. What is u dagger? That. What will be here? No, what will be here? Sorry.
A star.
A star. Good. What will be here?
C star.
Oh, how, where is C star? There are is only A and B.
B. It's B minus B.
Okay, what is here? It's A. Clear? Now what will be here? Minus B. What this will be? Clear? So take the dagger. What you will get? A minus B star and B here A star. Clear? So now multiply. Okay, so multiply. So it will be something A star zeta 1 star plus B star zeta 2 star. Okay, like this thing. Then the another. Okay, so another element like minus B zeta 1 star plus A zeta 2 star. Clear? So now compare the coefficients. Okay. Okay, compare the coefficients. So I am having therefore zeta 1 star prime. So that's equal to A star zeta 1 star plus B star zeta 2 star. What is zeta 2 star? So it's minus B zeta 1 star plus A zeta 2 star. Is it? Now compare first and second. So let's call this as second. Call this as first. So now look here. What is here? And then first element transforms this way. Okay, so that means zeta and zeta dagger does not transform in the same way under SU2. So this is a very important difference. Now if you take in the simple three-dimensional space the rotational group, you are having R and R transpose. They will transform in the same way. But that peculiarity is not here. Okay? So that is not true in this case. Okay, so let's say you are having a vector V or vector R, clear? And what is it is transpose? That is vector R transpose, clear? So if you take the components of the both vectors, let's say in O3, so they will transform in the same way. So let's say you are having XYZ and you take another XYZ, you will be having the same thing. But here, since there is a complex conjugation as well, so they do not transform same way. So look here, you are having zeta this way, okay, its transformation rule is this thing. But look here, the transformation rule is not same thing. Okay? What should be, when I can say the transformation rule will be the same thing? So you should be having here zeta 1 and zeta 2, and you should be having here zeta 1 and zeta 2, whatsoever are the elements here. Okay? So whatsoever is here, so you should be having at least what? Zeta 1 and zeta 2. Okay? Clear? So got it? So tell me, are these rules the same? So now let me write another object with the complex conjugation. Then maybe you can appreciate what is exactly. Okay. No. What I have said? So no, what you should be having? Okay. You should be having these coefficients should be same. I'm sorry. Coefficients should be same. Okay. Let me give an example. Then maybe you can understand it. Look here. So this is simply an example. So in two dimensions, how the components of the vector transform? X prime is equal to x cosine of theta plus y sine of theta. Y prime is equal to minus x sine theta plus y cosine of theta. Clear? So now if I take any vector, okay, in the three-dimensional space, how the components transform? So Vx cosine of theta plus Vy sine of theta, and Vy prime is equal to minus Vx sine of theta plus Vy cosine of theta. What is unchanged? What is unchanged? Cos theta, sine theta, cos theta. They are unchanged. Is it? Because they specify me the transformation rule. Okay, you replace x simply by what? Vx and y by Vy. Clear? So what is the transformation rule specified by? A, B, B star and A star. They should be the same thing here. You should be having A star, okay, A, B, something, okay? And, okay, so the vector, you just need to then replace the vector by the another components, clear? By its corresponding components. These coefficients must be same, but they are not same. You are having A, B minus B star, A star, they are the different, clear? So, okay, so let's take it another, okay, let's look at this very quantity. Okay. So let me take this very object. Let me define this very objective minus zeta 2 star. So let me check it. And zeta 1 star. Let me write this very object. Okay? And let's calculate its what? Transformation rule. So, since it's a column vector, how it will transform? Tell me, since it's a column vector, only having the complex entries, clear? So, how the column vectors transform? Now tell me, how the column vectors transform? So, let me define some, let's call this as, call a name for this thing, some zeta tilde, okay? Clear? So, let's call this thing. How the column vectors transform? So under SU2, okay, for U belong to SU2, so how this will transform? Zeta tilde will transform as some zeta tilde prime is equal to zeta tilde. Because it's a column vector, you just need to multiply it by what? U. Clear? Okay. So now what this object is? Zeta prime, it is minus zeta 2 prime star and you will be having zeta 1 star prime. Clear? With a prime index, okay, is equal to, what is this thing? It is A, B minus B star and A star. What is zeta? It's minus zeta 2 star and zeta 1 star. Clear? So I have constructed a new vector like this thing and it transforms under SU2 this way. Okay. So now let's compare the coefficients. Okay. Compare the coefficients. So you will be having minus zeta 2 prime star, that's equal to A minus zeta 2 star, okay, plus B zeta 1 star. Then you are having zeta 1 star prime, so that's equal to minus B, okay, minus zeta 2 star plus A star zeta 1 star. Let's call this as third. Okay, now look at the first and third. Look at first and third. Are the same? You are having A, B minus B, A star. What are the elements of this very objective?
Minus B star.
Minus zeta 2 star, zeta 1 star. Is it?
Minus B star.
Uh-huh. Yes, minus B star. Yes. Okay, it's minus B star. Clear?
सर बट यहाँ से हमें ना zeta 1 star ऊपर है zeta 1.
No, I have just constructed this kind of objective. It's simply, it is a definition. Okay? You got my point? What I am saying, I have constructed, instead of zeta dagger, since zeta dagger does not transform in the same way as zeta, what I need to do, I want to construct another vector which is having the complex entries, okay, but transform in the same way as zeta. So now look here, I have constructed this video. It is simply a construction. Clear? So I will just show you there is a nice way to write this objective. It is simply a construction, okay? And I have seen, okay, I have shown that this very objective transforms in the same way as zeta. समझ आया? Clear? So now if I write, okay, so let's define an objective, okay. Okay, so let me write a matrix. Eta is equal to 0, minus 1, 1, 0. Okay, so let's write this thing, and now let's write this. So zeta dagger I can write, sorry, zeta tilde I can write as 0, minus 1, 1, 0, and then zeta 1 star and zeta 2 star. Can I write it? Go खुश? Huh? Okay? So can I write it? Can I write it? Okay, so in other words, so I should have put, so let's put some name for it, right? So let me check. Okay, so if you see, this is simply a zeta star. Is this a zeta star? Is this a simple star, complex conjugation, not a dagger? So I can write it as eta zeta star without any complex conjugation. Sorry, without any dagger, without any transpose, sorry. There is only the complex conjugation but no transpose. If I take the transpose, that means it will become what? Zeta dagger. Clear? So now let's write it. Let's write. Rewrite what we have done. Okay? Let's rewrite it. You are having two objects at hand, the zeta and eta zeta star. Clear? So they transform in the same way under SU2. Is it? So their transformation properties are same. Okay, so what I mean by that, so under SU2, so zeta transforms in the same way as eta zeta star. Okay? समझना? So now let's take the dagger. So then I can construct a vector for dagger as well. Another vector for dagger which will transform in the dagger. Clear? Okay, so let's write. Then, so therefore, zeta dagger will transform in the same way as eta zeta star dagger. Clear? So now I need to simply take the dagger, okay? And you can check actually this eta zeta star dagger will have the same transformation rule as zeta dagger. Everybody is following it? Okay. So what this eta dagger is? So I can write it as zeta star dagger and eta dagger. Clear? Can I write it? Okay. So now eta is a real matrix. So it is dagger means simply what? It's transpose. Clear? So what is this object? So it is simply zeta star. Then dagger contains star and transpose. Star and star will go. It will be simply zeta transpose, eta transpose. So that means it is simply eta zeta transpose. Clear? So in other words, this zeta dagger will transform in the same way as eta zeta transpose. Or in other words, I can say eta zeta has the same transformation rule under SU2 as zeta dagger. Clear? So now let's construct the outer product. So which implies zeta dagger, zeta. So it will be same as, so eta zeta transpose zeta. Okay? So much, Yama? So now let's multiply. Sorry, no, not zeta dagger, it is an inner product, zeta dagger. So I have to construct zeta, zeta dagger. This is an outer product. So it is then zeta, eta, zeta transpose. Okay? Clear? Any problem? Now let's multiply this very object. So what is zeta? So it is zeta 1, zeta 2. So now what this object is? Let's multiply. What it will be? What is it? So eta zeta, so it is minus zeta 2, so it is something minus zeta 2, zeta 1. Clear?
Yes.
Is it true? So simply what is eta zeta? So it is 0, minus 1, 1, 0. What is zeta? Zeta 1, zeta 2. So how much is that? Minus zeta 2, then it is zeta 1. Clear? But there is a transpose. Huh? When you take the transpose, it will become a row vector, not a column vector. So how much is that? Now tell me. So it is minus zeta 1, zeta 2, then zeta 1 square, then minus zeta 2. Okay, zeta 2 square, then zeta 1. So what I have constructed? A matrix which will transform in the same way as what? Zeta and zeta dagger. Now what is that zeta dagger? If you remember, that contains on the diagonal zeta 1 square, mod of zeta 1 square, mod of zeta 2 square, and zeta 1, zeta 2 star, is it? So you remember? Huh? So now what is zeta? Yeah, zeta, zeta dagger matrix on this side. What is this objective? It is mod of zeta 1 square, zeta 1, okay, zeta 2 star, zeta 1 star, zeta 2 mod of zeta 2 square. Is it? Samashaman? Now that means this matrix and that matrix, they are equivalent under SU2. So their transformation properties under SU2 are same. Is it? Oh, Samashaman? Now what I have shown, I can show. Okay, so I have shown this left hand side transforms in the same way as the right hand side, or right hand side transforms in the same way as left hand side. But look here, the property of this very matrix, it's traceless. Is it traceless? So what is trace means sum of diagonal terms, is it? So it's a traceless matrix. I have shown under SU2 this very object can be converted to a traceless matrix. Oh, Samashyama? Okay, so this, be careful here. So there is one important thing. So we will get actually the meaning of what we are doing. Okay, what exactly we are doing. Now tell me, and this zeta dagger, it goes as what? U, zeta dagger, U dagger. Is it? Under SU2 it transforms this way. Clear? So, Samashyama? Now let me call this matrix on this side as minus H. H is not the Hamiltonian, it is some matrix. Clear? So what are the properties of this matrix? H is traceless. So now tell me, okay, H is traceless. This is the only property. Okay, so that means, now tell me what will be the transformation rule on the right hand side. So it implies, so if the left hand side transforms this way, it implies therefore H will transform as U, H, U dagger. Clear? समझ or minus H. समझ? Okay. Now tell me, if I make this kind of transform, what will happen to the trace of the matrix? It will be preserved. Okay. So now let's take the trace of this H. So that is same as trace of U, H, U dagger. What is that equal to? Trace of H, U dagger, U. So what is that? Trace of H. So it means trace remains invariant under this transformation. Clear? So trace does not change. Got it? So what we have done? Huh? Yes?
The trace of the initial left hand side matrix is equal to 0.
Yes. Okay. So here, if you see, you are having this matrix does not have a trace 0, is it? The zeta dagger does not have trace 0, is it? But under SU2, I have made we have made a transformation such that it is converted into what? A traceless matrix. Okay? So, think of the Pauli spin matrices. Okay? So you can convert one into the another, into a traceless matrix. So, by how? Simply by a unity transformation. If you remember the Dirac matrices, I have told you there, these, if you are having certain set of matrices, these kind of properties, you can always convert them into the Dirac matrices by a unity transformation. Got it? समझ आया क्या? Huh? Suppose if you are having, let's say in two-dimensional space, or if you are having set of two by two matrices, but their trace is equal to 0. Clear? Got it? You can always convert them into the kind of matrix like this, zeta dagger, by unity transformation. समझ आया? समझ आया? Okay, so in a moment we will see it. Okay, so this is all up to, so we have shown the zeta dagger and H has the same transformation rules under SU2. Clear? Okay, so now let's construct a matrix which is traceless. Okay, in two-dimensional space, let's construct another matrix which is traceless, which is the trace of the matrix is 0. So that will transform in the same fashion as this object. Clear? Because we have shown a traceless matrix under a unity transformation transforms this way. Clear? So, समझ? Okay, so now let me construct out of position vector. Let's construct a 2 by 2 matrix from the position vector R is equal to x, y, z. Okay. Okay. So with 0 trace. Huh? So let me write that matrix as H, this small h. So it is something sigma dot R. Okay. So this very. Okay. So let's write it. So this is a kind of matrix I have constructed. So there is a reason for why I have constructed it this way. You will see. Okay. Let's after I am finished with this thing, then I will tell you how we can construct. Okay, an operator in terms of the another operators, because H is a matrix and square matrices represent the operators. Okay, so let's forget that very term. So let's write it. What this is? It will be simply sigma x and x plus y sigma y plus z sigma z. Because this is the dot product of sigma. Sigma has how many components? 3 components, and R is having 3 components. Clear? So now let's write it in the matrix form. It is 0 x 0 plus 0 minus iy 0 and then plus z 0 minus 0. So now let's rewrite it. So which implies h is equal to what? Z x minus iy and x plus iy and minus z. Now tell me what is the trace of this very matrix? 0. So that means in under SU2 it will transform as U H U dagger. Clear? So now there is an additional property of this very matrix. It's a Hermitian. Is it a Hermitian? Check it. You can see it from here. X, Y, Z are real parameters and sigma X, sigma Y, sigma Z are what? Hermitian. Clear? They are the Hermitian matrices. So what we are having, H dagger is same as H and trace of H is equal to 0. Clear? So therefore under SU2 so therefore we have constructed a matrix H which goes H as prime U H U dagger where U belongs to clear? समझ आया? समझ आया? Okay. Now let's write what is so does trace preserve is the trace preserved here? Yes, because trace of H prime is same as trace of H. You can show it. Now let's write the determinant. Okay, so let's write determinant of H. So what we will get? Determinant of U H U dagger. Clear? Can we get? समझ आया? Let's write the determinant. Then we will see what exactly it implies. This kind of matrix, what it implies. Okay, why we have constructed this matrix in a two-dimensional space with the help of the Pauli spin matrices. Clear? So think of, okay, you can think this matrix in this way. So let's say you are having the electron. It's having how many components of the spin? 2 spin. So but it is also, the electron is represented by the position vector. In three-dimensional space, it is having the position vector. On top of that three-dimensional space, you are having a two-dimensional space, capturing the spin space of the particle. Clear? So now if you have to write the position vector of, let's say, up spin and the position vector of the down spin, how you will write that? In that fashion. Because up component will be having its own position vector and down component will be having its own component. Clear? So that means you are making a pictorial representation of the position vector in the two-dimensional space. Got it? Okay, so now let's write what is the determinant of H. Calculate determinant of H on. Okay, calculate determinant of H on this side. So what it gives me? What is the determinant? Minus Z square. Okay, then minus X square minus Y square. It is the determinant on the left hand side. Now let's write it. Sorry, I should have put H prime. So it will be X prime like this. Clear? It is H prime. So now what this is? It is determinant of U, determinant of H and determinant of U dagger. Okay, so now determinant of U dagger, so it will be 1. Since determinant of U is plus minus 1 and determinant of U dagger is plus minus 1, so ultimately it is 1. So it will be simply determinant of H. What is that? Minus Z square minus X square and minus Y square. What is that equal? So which implies therefore this X prime square plus Y prime square plus Z prime square is same as X square plus Y square plus. Now tell me what is this X square plus Y square plus Z square? It gives me the length of the vector, is it? Samajha? You got my point? So that means under SU2 the length of the vector remains same, preserved. Clear? Samajha? Now under O3 length of the vector remains the same thing. Samajha? So in other words, this H specifies me the position vector of the particle in two-dimensional space. Clear? Because its determinant gives you what? The length of the vector. Samajha? Samajha? Everybody followed it? Now what we have shown. Now tell me. What we have shown. We have constructed actually two types of matrices here. Okay, one is the simple, which has the elements as so which is simply this H, this capital H, is it? Samajha? Which simply gives me the matrix, this zeta zeta dagger or that zeta eta zeta transpose. Clear?
which has the transformation rule as the zeta zeta dagger. Clear? And then we have additionally constructed one matrix which gives you simply the length of the vector, is it? So when I talk about the length of the vector, so what does that mean? When I see simply the length of the vector in the usual three-dimensional space, is it? तो समझ आया? When we say that, so that means the length of the vector in three-dimensional space are the components of this very matrix. In other words, the components of this very matrix and the components of this matrix, they should be related in some way, because the transformation rules are the same. समझ आया? You got my point? तो आया मेन क्या समझ? We have shown the length of the vector under SU2 remains same, is it? So, or in other words, an SU2 transformation induces a rotation in three-dimensional space, because this is the length of the vector in three-dimensional space, and this invariance means actually there exists a rotation which preserves the length of the vector. Clear? So, what is the kind of that transformation? It's actually an SU2. And SU2 has actually induced this kind of rotation. But SU2 in its own spin space or in its own space induces a kind of rotation on this H, like this U at U dagger. Clear? So now let's try to identify the elements of this very matrix. Okay, so let me write. Then you can see actually the connection between SU2 and O3. Okay, so I am almost done. So how much is time? So we are done almost. So now let's write. So what we are having? So we are having this H. Okay, so how much is that? Now it is zeta 1, zeta 2 probably minus. So it is plus. Then what is this thing? So it is minus zeta 1 square, and this is zeta 2 square, and then you are having minus zeta 1 zeta 2, and you are having this H is equal to Z x minus Iy and x plus Iy and minus. Now identify since the elements of H and H. Okay? Samashima? You got my point? So now let's write what is. Okay, so in other words, we can write this way. In SU2 rotation on the zeta 1, zeta 2, this is same as an O3 rotation on X, Y, Z. Is it? Because SU2 induces your rotation. Clear? So it is having the same kind of properties. So we call, if you are having two groups, if you are having the same kind of property, then we call those two groups as isomorphic in a physical sense. Let's say if you are having the character table of the or the group table of two groups same. Clear? So what does that mean? Those two groups are isomorphic to each other. Or in other words, okay, physically speaking, if you are having the property of one group is identical to the property of the another group, then we can say they are isomorphic to each other, or their behavior is same. Clear? Or their behavior is identical. What does that mean? So now SU2 rotation in this very case, and it actually induces what? Three-dimensional rotation. Clear? Now how I can, now that means there must be a connection between SU2 and O3. So now you can think, okay, X, Y, Z, they are the elements of this vector in three-dimensional space, and zeta 1 and zeta 2 are the elements in where? SU2. Clear? Are in the two-dimensional space. Clear? So now let's identify the elements. So I can write therefore this Z has to be equal to zeta 1, zeta 2, X plus Iy, I can write as zeta 2 square, and X minus Iy, I can write as minus zeta 1 square. So what it gives me, let's calculate X. So that means X is equal to 1 by 2, zeta 2 square minus zeta 1 square, Y is equal to, so let's subtract the 2, So it will be 1 by 2I zeta 2 square plus zeta 1 square, and z is equal to zeta 1 zeta 2. So that means the elements of SU2 group, okay, Samashaman, and the elements of O3 are related by this kind of rule. Samashaman? So we'll take examples on this kind of isomorphism tomorrow. We'll see, let's say if you are having rotation in XY plane, you'll see an equivalent of rotation where? In XY plane in the two-dimensional space. Clear? So Samashaman, you'll see how those things are induced. And you will see one more pointer about the addition of the angular momentum algebra. Clear? Okay. So any question? Huh? So it's a little bit trickier to understand here. Once you just think over it. Okay. So at the last steps you should think. Okay.